you can have a carafe with genus 0. You can have a carafe with genus 1. And you can have a really cool carafe with genus 1. I have to say, this is the way that literature professors respond to best. They're far better drinkers than physicists. That's my experience for my own family. And of course, topology plays a role in body art, but I don't want to dwell on this slide too much. Yeah, there we go. We've seen it. We'll let it go. What about physics? In physics, usually topology comes in and came in for many years when we're thinking about vortices in one way or another. So think about the wind pattern in a clear day over the ocean. Nothing very interesting, right? Probably no wind. You can compare it to the wind pattern in a hurricane, where clearly the wind winds around the eye of the storm. And this makes hurricanes very robust because you have a topological defect that cannot go away on its own. It just has to run its course and do whatever damage it's going to do, and it's very painful. But there you go. That's a vortex, and that's a topological effect. For us, in condensed matter, we usually think about vortices in superconductors, where we put a magnetic field through a superconductor, and that creates a little hurricane of electrons doing supercurrents around vortices. And again, these are topological defects. They cannot go away very easily. Now, in recent years, topology started appearing in electronic physics in semiconductors. That was a bit of a surprise for me, but I guess many other people were smarter and saw it coming. But I wanted to, so let's see how this comes about. So the thing that gives topology in semiconductors is one culprit, the spin of the electron. So the spin of the electron has a direction, right? And we all know that we can write the wave function of the spin of the electron broken down into a two-tuple spinner. Psi up, psi down, the wave function for up electrons, the wave function for down electrons. And if you want to encode the direction into the spinner, you know that the top will be cosine theta over 2, the bottom would be e to the I phi sine theta over 2, right? So the spinner encodes the direction of the spin. The spins can wind, just like the wind in the hurricane. So when we think about, say, 1D wires, if they have spin-orbit coupling, an electron going to the right would prefer to point up, say. An electron going to the left would prefer to point down. Now, let's not think about the wire, let's think about the atomic background. Let's think about the electron moving in the background of the atoms that make up the wire. Then we know that the electrons will arrange themselves into bands. And here's one such band. It stretches from minus pi over a. A is the lattice constant to plus pi over a. And it's periodic. Despite the way that I drew it, I'm sorry I used PowerPoint rather than Mathematica to draw this curve. It's supposed to be periodic. And you can imagine that each momentum state in this band has an electronic spin direction associated with it, right? Typically, you have a band for spin up electrons and a band for spin down electrons. But here you have spin-orbit coupling. And each momentum, an electron in a particular momentum, might have a particular tilt, which is different depending on momentum. And that can wind. It can start pointing to the right, up, left, down, right. So in this example, it's like this quantum wire mapped this strip of momentum from minus pi over a to pi over a into a circle. What mediated that mapping? It was the spin. And that's a topological defect in the band structure. It's not in real space, it's just in momentum space. You can do the same thing. Oh, by the way, so this kind of winding is actually at the basis of a very important phase that a lot of us discuss nowadays. If you take this spin-orbit coupled wire, put it in proximity to a superconductor, if you're lucky, you might end up with a p-wave superconductor, and that would be the Kitaev model. And this winding of a pseudospin would give you two Majorana states on the edges. Now, I understand that next week Roman Luchin is giving a talk, and his talk is going to be on Majorana. So I'm under strict orders not to talk about Majorana fermions. So I'll move on from that to 2D. So how does this topology or topological defects of the spin emerge in two-dimensional systems? So think about a film. A film will allow electrons to have two directions of momenta, px and py, right? And for each momentum state, you can have, again, a different spin direction, right? So here's an example of a band structure. So a valence band and a conduction band as a function of momentum. Can you see the labels here, or is it too low? Should I use the other side? Other side? Sorry about that. So you can see that there's px, py, there's a valence band, there's a conduction band. And now each momentum state is going to be associated with a spin direction. For the experts amongst you, you can recognize that I can write a Hamiltonian that's like the Pauli matrices dotted with a three-dimensional magnetic field that's a function of two-dimensional momenta, px and py. And this magnetic field is now a function of momentum, and we can ask, does it wrap or not around the Bloch sphere? As we probe this as a function of momentum, does it wrap the sphere or not? And I'll draw this, it will become more obvious. So for instance, you can start looking at the gamma point, look at zero momentum. This magnetic field is pointing up. So think about it as the north pole of the Bloch sphere. As we look at bigger and bigger momenta, we're going to have the magnetic field, the spins, pointing closer and closer to the equator. As we increase momentum further, we can slip down to the southern hemisphere, and at large momenta close to the edges of the Brillouin zone, we'll end up with spins pointing in the opposite direction, with the magnetic field pointing in the opposite direction. So again, the spin took this two-dimensional space and wrapped it around the sphere using the direction of the spin. And this is the basis of two-dimensional topological insulators. What's the benefit of having this wrapping in two dimensions? In one dimension, I'm not allowed to talk about it because it was the Majorana fermions. In two dimensions, I have complete freedom, right, Kirill? In two dimensions, this wrapping results in what we call a two-dimensional topological insulator. So if you have a sandwich, say, so maybe I should go back a second and just say that this physics that I just explored, it was realized by Andrei Bernovic, Taylor Hughes, and Xusheng Zheng, that it could apply to two-dimensional semiconducting heterostructure with strong spin-orbit coupling. And they said, if you have a mercury telluride sandwiched between two cadmium telluride layers, two dimensions, it's completely boring semiconductor. Except if you make it thick enough, thicker than 6 nanometers, this boring semiconductor becomes a topological insulator, and it grows edge states. What do I mean? Think about this two-dimensional, from a different perspective, the two-dimensional sample. It's semiconducting, there's no electrons moving inside, but then as the thickness of this exceeds 6 nanometers, there are edge states appearing. Electrons appear to be moving freely around the edge, spin up electrons going in one orientation, spin down electrons going in the opposite orientation. And these are two-dimensional topological insulators, and this was indeed measured by Lawrence Molenkamp group in Würzburg. Now, you see I have a bit of a retro color coding here. So I was looking to see what kind of modern renditions there are of edge states, and of course there are. So here's the more glossy description of this edge states. Spin down electrons going one way, spin up electrons going the other way. And there's even a description of topological edge states, especially made for Los Angeles Basin residents, the freeway version of the edge states. Spin ups going on the right lane, spin down going on the left lane. Clearly, this was not done in Los Angeles, though. You know how I know, right? What? Not moving. No cars. Freeway is free. That's no way. What can you do with these topological insulators? We don't know yet completely. Maybe spintronic devices, maybe dissipationless leads, maybe Majorana fermions, but I'm not allowed to talk about them. What I want to talk about is what happens when you combine these topological ideas and light. So if you take a semiconductor and shine light on it, what can we do? I'll show you that maybe we can induce topological behavior in semiconductors that are otherwise trivial, giving you a knob, an instantaneous knob, to create topological spectrum and edge states. Maybe we can make special topological photonic states. In this case, it will be topological polaritons. Maybe new paradigms for infrared detection. So this would be the quantum devices that maybe can arise from topological behavior. And lastly, it might suggest new paradigms for controlling photons using topological ideas. So those are the things I wanted to show you. But whatever you do, what you want to do is to turn on the light on the material. Sorry. Couldn't resist. Any questions so far before we dig in? Anything? Feel free to stop me. All right, so the first thing to do is to ask, can we induce topological behavior in a non-topological semiconductor? So you have a boring semiconductor. It has some spin-orbit coupling, but when you probe, I'm thinking about a two-dimensional semiconductor, a film. When you probe the spin as a function of the two-dimensional momentum, the spin is not doing anything interesting. It may explore some pieces of the Bloch sphere, but it will start at the North Pole, it will end in the North Pole, there will be no wrapping. It's like a trivial geometry for the spin. It just maps the plane to a point, basically, topologically. I'll show you that actually with light, you can induce this to become topological. So if you turn on the light, what happens? So here's the valence band, the conduction band. There's a spin direction in the valence band. There's the opposite spin direction in the conduction band. This describes a non-topological situation. Spins point up over here. They also point up over here. And now we shine light, frequency omega. It creates resonances between the valence band and conduction band, right? It can excite electrons to the conduction band. If the light is coherent, we should think about these two bands, and these are cross-sections of those bands, as coming together. Like rotating wave approximation is the keyword for that. And in PowerPoint, it's very easy to bring them together. Just goes like this. And then these photons, they create direct resonance between states in this ring and that ring. Rotating wave approximation makes it look like we have a direct matrix element between those states. And whenever we have direct matrix elements, we create a new gap. Right? So light can create band inversion. Now let's scrutinize what would be the spin direction in the new valence band. So now instead of looking like the paraboloid that I had before, now it looks like some kind of a dormant volcano with a crater. If we go far away from the crater, we're probing spins far away from the resonance, they point up. And again, this is a cross-section of this object. But if you look inside the crater, well, what is this inside of the crater? It's really the bottom of what used to be the conduction band, right? And then the spin is inherited from the center of that band. And therefore, it has to point down. So if you start over here in the North Pole, you end up over here in the South Pole. And the only question is what happens as you probe the resonance ring and ask, what's the direction of the magnetic field around there? Does it wind? Does it not wind? If it winds, then you created a winding of the spin around the sphere, and you create a topological phase. And guess what? With spin-orbit coupling, it'll wind. And you'll get a topological phase out of this boring semiconductor. So looking under the hood a little bit, for the experts amongst you, you have two bands. So let's mark the bottom band with tau z equals -1, the top band tau z +1. Then we can write a new Hamiltonian relative to this resonance point, kinetic energy minus omega over 2. It's like the distance between the states in this ring. Band up, sorry, top band, bottom band, tau z +1, -1. And then there's a matrix element from the drive that connects the two bands. That looks like tau x, tau y pieces with the real part of a number g and an imaginary part of a number g, giving you the x and y components. What is this g? It's just the matrix element between the conduction states and the valence states. And again, with spin-orbit coupling, what this number, this complex number does at the resonance ring, as we look at what this complex number is in momentum that corresponds, the momentum that corresponds to this ring, that poor complex number is going to wind, this is this red arrow, it's going to wind around the origin of the complex plane. And that what gives us this topology. So if you have this, plus the fact that your spin goes from up at large momenta to down at low momenta, going from the North Pole to the South Pole, and you know that at the waist, at the equator, it wraps around the xy plane, you know that you surrounded the sphere. It looks like a lot of hocus pocus with all those arrows drawn in Mathematica and PowerPoint, so we have to do a simulation. So here there's a full wrapping in tau space, not exactly the spin space, but same difference. It's the topology emerging from the spin structure. Okay, so you can take a film like that, you can discretize it into a lattice, simulate the Hamiltonian that we had before, get projection along the x-axis of the band structure. Here's the valence band, conduction band. And now you can irradiate it, put a perturbation that mixes the two bands, and see what happens with exact generalization. And this is what happens. You get this volcano. This is the band structure projected. You get a new valence band, a new conduction band, a new band gap. And look at that. What are those lines? This was diagonalizing this sheet of this film with periodic boundary conditions over here, but open boundaries over here. These are at states. One line corresponds to left-moving states, and the other line to right-moving states at the other side of the sample. So this is the Fouquet topological insulator that Victor Galitsky, Nate Lindner, and I worked out some 8 years ago in parallel to works by Oka and Oki in a graphene setup. Questions? This was my first exposure to topological light, if you wish. And I went and gave talks about this. I was very happy about this, like this, here it's nice to describe the light like a lightning, and then you can say that somebody who produces the lightning is very happy. It's like Zeus is very happy with the result. I was very happy with the result. I went out and gave talks about this. Every time I gave a talk, people told me, okay, look, so what are you doing? You're taking a quantum well, you're shooting a lot of light over it, it's going to melt, it's going to heat up, you're not going to see anything, all your electrons are going to run away, what are you talking about? And then, part of my research program was aimed at showing that actually you can stabilize thermal states in irradiated interacting semiconductors, but that's a whole different talk. At the same time, I started thinking, maybe these people are right a little bit, maybe I should think about, can you get similar topological states, not with a lot of photons, can you get it with one photon? So you can imagine one photon. You can imagine having one photon producing a particle-Hall pair in the sample, and maybe doing some Rabi oscillations, being absorbed into the exciton, exciton emits into a photon, photon emits into exciton, such that it stays on the edge, just like the edge states that I saw in the Fouquet topological insulator. Now, here you really see the challenge of me animating this, because really you should think about light, which are those two kind of wavy lines over here, being absorbed by the material, creating a particle-Hall pair. And then the particle-Hall pair emits a photon, the photon gets absorbed. So these are Rabi oscillations between exciton and photon that stay on the edge. But I can't really oscillate them very well, so I apologize. But now what is this? So a particle-Hall pair is an exciton. A photon, we know what it is. If you combine exciton and photon, that's called a polariton. Now what I want to create here, inspired by this Fouquet topological insulator, is a topological polariton, which, of course you can call it a topolariton. Rolls off your tongue. If you have a name like that, you have to work out the theory. So let's see. So let's see if this exists. And this seems to exist. So let's construct it. What's the first ingredient? First ingredient is excitons. What are excitons? If you have a quantum well, you shine some light on it, it can excite electrons from the valence band to the conduction band. And then Coulomb interactions can make the electron be bound to its hole and propagate together. Here's the propagation together. I managed that in the animation. Now, this is a bosonic particle, and it has a dispersion. It has a gap. It's a little bit under the band gap of the material because of the Coulomb attraction. And as you give it more momentum, it'll have more energy, and it can start moving. So in 2 dimensions, there's a dispersion. This is the cross-section of it. That's ingredient 1. If you want a polariton, you want this exciton to interact, to hybridize with light, and you want the light to have like a strong field. So how about let's confine a beam of light between 2 mirrors, make it into an optical cavity in 2D. And such optical cavities also have light modes native to them. They also have a dispersion. So frequency of the photon is a function of momentum. It will tend to the speed of light at large momenta. At small momenta, well, there's a little bit of a gap induced by the discreteness that the mirrors induce. That's the photon component. All good? Now, at least in PowerPoint, I can take my quantum well, put it between those 2 mirrors, and combine the excitons and the photons. Photons, excitons. And when those 2 dispersions meet, there's a matrix element, right, They can make the exciton into the photon into the exciton. They hybridize, and there's an avoided crossing. And then you end up with a lower polariton band and a higher polariton band. And they oscillate together. Again, the photon should dim as the exciton comes into play. The exciton needs to dim as it emits a photon. It's not really the two of them in parallel. They oscillate, right? Do you see what I'm saying? It's like you oscillate between this particle, this polariton oscillates between being a photon and being an exciton, back into a photon, back into an exciton. That's what this hybridization means. All right. Now, where's topology? If I think about this as a two-band system, right? Or I just think about this degree of freedom, are you a photon or an exciton, as a spin half degree of freedom, I can think of describing this in terms of Pauli matrices again. Say tau z being +1 or -1 means whether our excitation is an exciton or a photon, right? And it seems like in this diagram, we start off, so if you look at the lower polariton state, we start off with being a photon, right? That was the low energy thing, and then the photons shoot up, but this band becomes from a photon to an exciton. So it's like the spin going from the south pole to the north pole as a function of momentum going from small momentum to large momentum. Again, looking under the hood and thinking about the Hamiltonian, these bands are described by a piece that says what's the energy difference between being a photon and being an exciton multiplied by whether we are photons or excitons, and a hybridizing matrix element between the photon and exciton. We already guaranteed that this band will go from photon to exciton. What do we need to get topological bands? We need this number, this complex number, to just wind around the origin. So this is a cut in momentum, but you can imagine that there's a ring of resonance, and apologies that I don't have the proper mathematical plot of that. On this ring of resonance, so this is absolute value of momentum, but if you think about the direction of the momentum, you see this arrow to the right, it needs to wind. It needs to point in all directions. That will cover the equator of the Bloch sphere, and we'll get topology. And guess what? If you have spin-orbit coupled materials, you will get this winding at the ring of resonance between excitons and photons, exactly the same way as you get in a Fouquet topological insulator. What's the result? Well, you need a third ingredient for topological-polaritons. You need a periodic potential. Just again showing the X-ray, you see you have two bands, right? But they overlap in energies, right? That's generic. I want to have edge states from the bottom band to the top band, but I need an energy window where they appear, right? So I'm using a third ingredient, a periodic potential that will open these gaps, a periodic potential with a wave number that corresponds to the wave number at which the exciton-photon resonance happens. It's too much details, doesn't really matter. You can simulate something like that. A band of excitons, a band of photons, cavity photons, and this periodic potential, and this is what you get projected. So this is, again, diagonalizing a Hamiltonian on a cylinder. You get a bunch of bands because of the periodic potential. And what do you get between the bands? Check it out, edge states. Red is one side of the cylinder, blue is another side of the cylinder. And there's three-dimensional rendition of the same thing, shows you how you split your band structure, split your bosonic, polaritonic band structure into a bunch of bands with different Chern numbers. What are those Chern numbers? It'll come up in a sec again. How many times does the spin wrap around the sphere? If it goes one way, it's Chern number 1. If it goes the other way, Chern number -1. If it wraps twice, Chern number 2, and so forth. And between bands with different Chern number, you expect to see those topological edge states. So what are they? In this case, it means that if you shine light at the sample, at the frequency corresponding to this gap, the light will stick at the edge of the sample, become a polariton, and just move around it before decaying into bulk bosonic modes. This could lead to photonic isolators, photonic diodes, for instance. And the question, can you realize this? It seems like the realization of this will depend on how strong of a potential, a periodic potential you can give to the system. We estimate that 1 MeV is about right. It's 10 Kelvin, which means that the topological gaps that emerge would also be of the order of 10 kelvins, 1 MeV. And good material candidates for doing this is transition metal dechalcogenides in a magnetic field. I have to say, every time that I say transition metal decalcogenide in a talk, I get scared. So this is like the part that I practice the most. Just say decalcogenide. The only problem is that 2 days ago, I gave a talk in a movie review that had not transition metal decalcogenide, but transition metal tricalcogenides. And I realized that I didn't practice tricalcogenides hardly enough. And of course, it got stuck in my tongue. Anyway, so transition metal decalcogenide films in a magnetic field can give you the semiconductor element. You stick them in a cavity, and I think you should, given the right parameters, you should see these topological polaritons. What about topological devices? So maybe topological polaritons, maybe topolaritons can lead to devices. Unlikely. We need something a little more direct. So here's the thought on three-dimensional topological insulators. We didn't talk about how they arise, but we can talk about the properties. If you have bulk three-dimensional topological insulators, the feature is on their surface, they're boring semiconductor into the bulk, but on the surface there's an electron gas. That electron gas looks like a Dirac cone. What does it mean in layman terms? It means that there are electrons that move freely on the surface, and they're completely spin orbit locked. What do I mean? If this electron wants to move to the right, it has to point perpendicular to the direction of the motion. When this electron moves, you see, it's also pointing perpendicular to the motion. This electron spin perpendicular to the direction of the motion. So the spin is a function of momentum. It's a little harder to see in this graph, but it wraps around the bands, the valence band, the conduction band, in such a way that it's always perpendicular to the group velocity. Full spin orbit locking. It must be good for something. What is it good for? Well, it's a gapless spin orbit coupled Dirac surface gas. Maybe it's good for Majoranas, but I'm not allowed to talk about it. Maybe it's good for infrared detection. So if you shine light on it, maybe you can make detectors out of it. Infrared detection is kind of tricky. Well, for several reasons. First, it's politically tricky because the biggest use probably for infrared detection is night warfare. But we'll not talk about that. There's another use, which is kiddie spy toys. So we can think about that as a good use for infrared detectors. And it's also used in science all over the place. What do we have in terms of infrared detectors? So red is 780 nanometers. That's where red stops, right? Anything with larger wavelengths is going to be infrared. So here you have 1 micron, 2 microns, all the way to 17 microns. And these various curves are the efficiencies of detection of various infrared detectors. You see, most detectors crank out, they just die out at around 6 microns. There are two materials that, when cooled to liquid nitrogen temperature, can detect reasonably well up to 16 microns. Why is it so hard? It's because I think my understanding of light detectors, those are semiconductors. And as light comes in, it excites electrons, it creates excitons, and we measure those excitons. So if you have photons coming in that are sub-gap, they won't create excitons. So we won't be able to measure them. So we need low-gap semiconductors. Actually, I don't know if it's easy to see, but what are those semiconductors? MCT. Oh, that's mercury cadmium telluride, which you may remember from my topological insulator slide. You have other topologically sounding things here, like indium arsenide, indium antimonide. These are not topological infrared detectors. They're just alloys that have a small band gap. They're close to a band inversion, which is what made them become topological insulators in a different part of their life. Okay, so this is the problem with infrared detection. You don't really have anything past 16 microns, and certainly not in room temperature. You have to cool this device. Why? Room temperature is around 300 Kelvin, right? Black body light at 300 Kelvin is here, 10 microns. So you can't measure something that you yourself emit in abundance if you're a camera at 300 Kelvin. All right, so let's see. Actually, what's the time? Where's the clock? 4:20 right now. 4:20. So I have another 20 minutes or so, right? Or what? 30 minutes. 30 minutes. Okay, no problem. We can do it. We can shoot for 50 minutes. Okay, you can press me a little bit. All right. So can we use topological insulators to do better? This is the dispersion of the surface gas of electrons in the boundary on the surface of a three-dimensional topological insulator. It has no gap. So maybe it can detect actually photons with even a larger wavelength than this. That's the motivation. Maybe the gaplessness of topological insulator surfaces is the thing that could be crucial. Well, so we tried to think about that. And again, my partners in crime here are Nate Lindner and Felix von Oppen. So we started to think about what kind of currents irradiation of a surface of a topological insulator would give. No matter how you want to calculate it, you end up calculating a Fermi golden rule that tries to understand how electrons can go from here to here absorbing a photon. And no matter what you do with your Fermi golden rule, it will end up with a current that's quadratic in the electric field that's applied and inversely proportional to the frequency squared, and has some relaxation time tau in front. Right? Kind of makes sense, right? The electrons get excited, they move somewhere, and then they relax and they stop moving. And we're neglecting Zeeman coupling here because the Zeeman coupling is so weak. Now, so we went ahead and calculated this matrix Q that tells you how big this response is in dimensionless units, and guess what we got? 0, nothing, despite papers that were online that claimed otherwise. You just get nothing. That was very disappointing. But then we thought maybe we went at it the wrong way. I mean, we used circularly polarized light. We did the right things. I think we got 0. But then we thought, well, really what's special about the surface topological insulator is that, you know, the spin-orbit coupling is so perfect. Spins move perpendicular to the, the electrons move perpendicular to the spin. So naively, you would think that as light comes in and hits the surface, electrons absorb the light and just scatter it to all directions. No directionality, no current, they just heat up. But now, because of the spin-orbit coupling, maybe we can use a magnetic field to tell them where to go. That was the thought. And in parallel, there was a group in North Carolina that was thinking along the same lines. Now, so we want to use some spin-orbit coupling to shepherd the electrons. So wait, before I show you this, I need to say, we want to grow the effect. We have no current, we want to grow the current. And if you want to grow something, you need to learn from farmers. They know how to grow things. And farmers grow things in rows. There you go. Now you can look at it. Now we thought maybe we plant rows of magnetic materials on the topological surface, and those rows will tell the electrons where to go. And that actually was true. So if you look at circularly polarized light hitting a surface topological insulator that's patterned with an alternating magnetic texture, your Hamiltonian, again for the experts, you get the spin-orbit coupled piece of the Hamiltonian, and then you have an oscillating Zeeman field. That Zeeman field actually makes electrons respond by just moving along the rows. They'll move up for circularly polarized, for right circularly polarized, they'll move down for left circularly polarized, and so forth. We set out to calculate how big the effect was. And again, there's some formula. There's a current in the y direction. It depends on the intensity of the light at various frequencies. Omega squared in the bottom, tau here. Some combination. So one thing to appreciate, the distance between the magnetic pattern determines the sensitivity, which wavelength you'll be sensitive to. So you can make your pattern in such a way that aims at a particular wavelength. And for 10 microns, I think it'll end up being 10 nanometers distance. To see 10 micron infrared light, you need about 100 nanometers between those lines. And then there's a function, a dimensionless function, that tells you how you respond to various frequencies. And different temperatures, you'll have a different response, right? So just looking at the peak response as a function of temperature, with temperature of the device normalized by the black body temperature of the radiation you're trying to see. 10 microns means 300 Kelvin. You see that 0 temperature, we have a certain efficiency. You go to the black body temperature, it only dropped off by 40%. So this technology could actually detect infrared light, possibly, at a temperature where thermodynamically you shouldn't be detecting it. Of course, this is the non-equilibrium situation, so we're not bound completely by thermodynamics. So this seems to be promising as maybe a room temperature infrared detector. Okay, maybe this is the use of topological insulators. Then we started talking about this with Patrick Lee and Chris Chen, and they said, well, how about maybe let's do something better. In 3 dimensions, there's another material that's gapless. It's vial semimetals. Vial semimetals, well, I'm trying to depict them. Think of a box of a material, but now think about the dispersion. Think about the band structure of the material in terms of 3-dimensional momenta. But I can only draw 2-dimensional momenta. So again, 2-dimensional momenta and energy. And what these materials have are points where the energy is 0. As you look at momenta around them, the energy grows linearly. So it looks like a Dirac cone, except that it's in 3 dimensions, so it's called a vial node. They usually come in pairs, and they have this dispersion that looks like this Dirac cones, and also perfect spin-orbit locking. Now, on the surface, these topological materials have an arc states. So it's like a sheet of electrons winding around the material, giving you an extra surface conduction channel. It goes in one direction, currently about the material. So we're starting to think, what happens when you irradiate such materials with light? Can you get them to give you a current instead of just heat? Now, if you just look at the vial node, and I'm drawing it again as a function of 2-dimensional momenta, energy in the 3rd dimension, you try to irradiate, you try to create a resonance, you'll have a sphere of resonating state where electrons can get excited to the conduction band. A sphere, not a circle, because this is a 3-dimensional material, right? So I'm just projecting. It doesn't look like the electrons will go anywhere special, right? They'll just go in all directions. And the pink arrows are the direction of the spin in the various momentum states. But actually, this is a very idealized vial semi-metal node. It's an isotropic vial semi-metal node. It's spin orbit locked, so it has like momentum dot sigma. But actually, most vial nodes are not isotropic. They're tilted. And if you have a tilted node, it looks like this. And now when you ask, if you shine light with a frequency omega, where will the resonance be? Well, it won't be in a horizontal ring. It will be in those green rings that hang in some way. Kind of like hoops around like a cone. Now, if the chemical potential cuts through this ring, you'll be able to excite electrons from this region to the top band, but not from this region. And the electrons excited would want to go in one direction and not in another. That was the principle that we were trying to use in order to make this into an infrared detector. Now, there's a Hamiltonian associated with it. There's, again, the sigma dot p. It has a certain chirality. And then there's the tilt, but I don't want to go into details of that. I think the diagram is sufficiently clear. Questions? When I say clear, I think I need to ask for questions. Yes?
So this kind of photon-like topological effect, do you need to pattern the magnetic structure like ribbons on top of it?
No. So for the vial semimetals, we just thought about the material itself.
Or as long as the node is tilted?
Yeah, as long as the node is tilted. So this will give you an effect just from the bulk. The bulk absorbs, like first 100 nanometers, the light comes in, gets absorbed, it creates some current in each node. Other questions? Yeah, sure.
So will the nodes be in pairs? Like if another node, will another node create an opposite effect? Or?
Yeah, yes. So this gives a directional current. But those nodes come in pairs. That was why it was important for me to show you this vial box with a pair of nodes. They cancel. Okay, so this is the generic Hamiltonian for a vial node with a tilt and chirality, no details, but the tilt will result in one current response to light. The chirality will result in another current, electrical current response to circularly polarized light. You'll need to remember that. But now, inversion symmetry actually dictates that both of these terms change sign when you look at a vial node, which is at some finite momentum, and a partner vial node at the opposite momentum. So if both these things change sign, obviously the electrons are going to move in the opposite direction, and the current will go away. However, if you have a material that doesn't have inversion symmetry, if it breaks, if it's non-centrosymmetric, it may still have time reversal. Only one of these terms, only the tilt, actually changes sign. but the chirality does not. And because you have two nodes with opposite chirality, one of these responses survives, the response to circularly polarized light. If you don't have time reversal and you don't have inversion symmetry, both survive. So yeah, I'm just saying this. So the chiral response survives with time reversal. Both responses survive. So linearly polarized, circularly polarized, everything survives if you have no time reversal symmetry and no inversion symmetry. Okay, so just to give you an idea of numbers, so it seems like we can engineer topological insulators to be sensitive infrared detectors. Now, for the experimentally savvy amongst you, think about irradiating with a mighty beam of 10 to the 6th watt per meter squared, so a megawatt per meter squared. I know it's a lot. And think about like a wavelength of 15 micrometers. If you do that, if you just look at bare TIs, there are some Zeeman response that's very small. It will be on the order of 10 to the minus 5 amps per meter. So bare TIs, I mean surface of a 3D TI, topological insulator. If you pattern the surface of this TI, as I was suggesting, you can get it 2 orders of magnitude larger, 10 to the minus 3 amps per meter is a response to this. If you look at the vial semimetals, so a layer of about 200 nanometers of vial semimetals, you would get an addition 2 orders of magnitude. This is for 0 temperature. So it seems strong and robust. If you ask about, so 2 things to say. If you ask about the room temperature response for vial semimetals, it will be suppressed 2 orders of magnitude, not because of the sensitivity function that I showed you before, just because scattering time. The scattering time of electrons becomes very short at high temperatures. It's just more phonons that scatter them, etc. But it's still very substantial. And then tantalum arsenide or molybdenum telluride, tungsten telluride could be good candidates for probing this physics. And in fact, there was some probing of this physics. Yeah, so how do I want to say this? First, I want to say that I'm aware that, looking at all those vial nodes, I'm made aware that time is running out. But actually what I was looking for is this statement. That there were experiments by Nuggetix group and also by Ken Birch and Dean Grant groups that showed the strong response to infrared of this Dirac, of these vial nodes. And they were relatively, Nu was measuring relatively thick samples, so you didn't see this large enhancement. Ken looked at narrow samples and did see this large enhancement. And also added to it that there might be a response due to shift currents. And after the talk, if you want to ask me about this, I'm happy to answer. But yeah, when I look at this, it always reminds me of a Sen clock. Questions about this devices part?
Is it possible to calculate detectivity?
Yeah. Somewhere down after the conclusion, I have a slide with the detectivities.
Okay.
So I can show you it later, maybe. But the upshot is that the detectivity of this guy matches Mercad at 30.
Lower frequency.
Yeah, at lower frequencies. At 30 micrometer and at room temperature, you beat mercury telluride. So 30 microns, you don't have anything to compare to. But you compare to the 10 micron detectivity of mercury telluride. What? You have bolometers, so nothing electric. Nothing electronic, nothing that relies on fast electronic response. What?
Not as good as a bolometer.
Not as good as a bolometer.
But you don't have to cool.
But you don't have to cool. That's the sales pitch. But it seems like so the detectivities are either matching. So at 0 temperature, they are an order of magnitude down from what's on the shelf right now. At room temperature, there's no competition anymore. And this was a comparison done for these guys. These guys are better even. But you can layer these. If you're really eager, you can layer them. Anything else? So there's another chapter in this talk that I wanted to give that I'm actually the most excited about. So one thing that we came across is the idea that if you have a periodic drive, also known as Fouquet drive, you can think about it as actually as giving an extra dimension to the system. We call those synthetic dimensions. Now I tried to find like graphics on the internet that brings home the idea that a periodic drive gives you an extra dimension. And the best I could do is this. Have you seen this show? I mean, when I was a child, it was playing in Israeli TV. Actually, this is fake color. It's really black and white. And this Time Tunnel was this. It's a really nice show. So if you get sick of House of Cards or things like that, and you're looking for some old classic, I recommend it. Now, I think the idea was here to show that a periodic structure in space allows you to travel in time. What I want to say is the opposite. A periodic structure in time feels like you're traveling in space. But that's the closest I could get. I'm sorry. Yeah, here's some more proper footage from that show. I think let's date back to the beginning of TV or something. Right. So the idea is that synthetic dimensions created by periodic drive could be like new control paradigms. Could give you new control paradigms for photonic states. So let me show you an example. So just a bit of introduction. Think about periodic drives. Think about a system like a spin that's driven by an oscillating magnetic field, say. And think about the slow drive regime. Namely, this Hamiltonian has energy scale that far exceeds the frequency of the drive. So very low frequency drive, kind of like a diabatic limit slow. You can imagine that the dynamics of this wave function, the wave function dynamics of this system can be broken down into harmonics of this drive. Each harmonic, e to the in omega t, will have a wave function associated with it. You take this ansatz, you just stick it to time-dependent Schrödinger equation, and what you get? Something that looks like a Schrödinger equation on a tight binding lattice, where each lattice site is n. But what is the n? It's the number of photons that you took from this periodic drive, the number of energy quantas that you took in. One caveat, if you took in an energy quanta, you have some extra energy. So actually, this extra dimension has to be tilted to make sure that you keep track of the energy of the photons, of the quantas that you took. But be that as it may, this drive looks like a synthetic dimension, in the sense that that dimension is the number of quantas that you took from the drive. It's like an extra space dimension that goes on top of everything else. Can you do this in 2 dimensions? Why not? I'm not a mathematician. I don't have inhibitions about these things. If you have a 2-frequency drive, you have 2 beams that drive your system, maybe you can expand your wave function in harmonics of both drives, n1 omega 1t, n2 omega 2t. Now this n1 and n2 act like 2 dimensions, 2 spatial dimensions, and sure enough, if you stick this into Schrödinger equations, you get a tight binding model on a 2-dimensional lattice with a force. The force is omega vector, omega 1 in the 1 direction, omega 2 in the 2 direction, because this is the energy that you get from the drive, n1 photons omega 1, n2 photons omega 2. Because of conservation of energy, whatever your system is, it will be confined to go on a perpendicular strip to this omega vector just so that it conserves this energy. It can't take too much energy, it can't give away energy, it has like a finite bandwidth. So the motion will be confined in this fictitious synthetic space perpendicular to the frequency. This is the construction I want to make. It looks pretty artificial, but you can do it. And in fact, there are other works that me and Ivar Martin were involved in that looked at whether this is well defined or not and what other things you can do with it. But I won't talk about it too much. But again, if you're curious, ask me. But right now, it just looks like a way of solving these equations that constructs 2 extra dimensions. What can I do with this? I'll do the following magic trick. I showed you what a 2-dimensional topological Hamiltonian looks like, right? It has some kind of sigma matrices multiplying momentum, 3-dimensional vectors that depend on 2-dimensional momenta, kx and ky. Right? You can believe me that a Hamiltonian like this creates a band structure that's topological. I'm going to take kx and turn it into omega 1t, and ky turn it into omega 2t. And pretend like this is really 2 drives, omega 1t and omega 2t. Same Hamiltonian. I just make kx into omega 1t, ky into omega 2t, and what do I get? It's the same Hamiltonian, but now it describes something completely different. It describes a spin that's driven by 2 coherent classical light beams. One omega 1 beam and the other omega 2 beam. And it's just the 2 beams are elliptically polarized. That's the only thing. The spin, but the spin will carry out a topological motion because it came from a topological band structure that will result in the following thing. One beam will be cannibalized and its energy will be pumped into the other beam. So one beam will come out strong, the other beam will come out weak, and the rate of work that the beam that drives this will do will be a topologically universal number. It'll just be omega 1 times omega 2. That's what I'll show you. So this might be a new paradigm for converting frequency and maybe amplifying frequency that we don't have good control on. So let's see how this works a little bit. So I won't be able to get into detail, but I can give you a flavor. So if we think about two-dimensional topological band structure, two-dimensional band structure. Sorry, the labels here moved a little bit. I didn't notice. Okay, so think about the Kx and Ky band structure that I had before. It has two bands, valence band, conduction band, right? And now the motion of a particle in such a band is going to be described with an anomalous velocity. What do I want to say? If you look at the velocity, so the ndt, in the synthetic dimensions, right? So again, I'm going to confuse it a little bit between real space and fictitious synthetic dimension. Don't be too confused. For now, let's think about them as the same thing. If we think about motion in two-dimensional space with a band structure like that, then the motion will be dictated by group velocity, that's just gradient of the dispersion, plus an anomalous velocity. What is the anomalous velocity? It's the Berry curvature that just measures whether the spin covers the Bloch sphere or not, cross the force. This is an analogy to a magnetic field cross the velocity that gives you a force. It's just momentum became space, and space became momentum, force became velocity, velocity became force. This is what's called the anomalous velocity. This is the Berry curvature. And what is the Berry curvature? An average is the Chern number over 2 pi. Just how many times does the spin wrap around the unit sphere, the Bloch sphere, as you probe it in the band, as the diagrams that I showed you in the beginning of the talk. So now let me try to PowerPoint simulate the motion that a particle in some momentum state in the bottom band is going to carry out, right? Now, moving to this time-dependent degrees of freedom, I took Kx. So this is the Brillouin zone. This is a map of the Berry curvature. Light colors are high Berry curvature. The integral of the Berry curvature is going to give us 1 over 2 pi. Kx, we said, becomes omega 1t. Ky became omega 2t. So it is like I'm applying a force to this poor particle. It's going to take it through the Brillouin zone over through these lines. As the particle will go over large Berry curvature regions, it's going to move in real space, in the synthetic dimension, perpendicular to the force. So what is the force? K dot is just this omega. So here's the animation after all this preparation. So the particle is going to go through the various momenta, and every time that it goes through this Berry curvature, it moves a little bit. Where? Perpendicular to the force along this strip that conserves energy. What decides which direction it goes? Does it go up or does it go down? Depends on whether it's in the bottom band or in the top band. Now, really, I'm describing a spin irradiated by 2 beams, right? It can point downfield for the instantaneous field or upfield. Downfield will correspond to the lower band, upfield to the upper band. Low energy state, high energy state. But wait a second. This motion means that we took n1 photons and we gave n2 photons. So the spin is really converting photons of one beam into photons of the other beam. That's what this motion gives you. It took me a while to do this animation. It took me even longer to explain it to you, so let me run it again. As the particles go through the momentum space, according to the winding dictated by the drive, it climbs up the strip whenever it hits this magnetic field, this effective Berry curvature, dual magnetic field. Questions?
Is it going back? Really, the particles in real space is going back and forth.
So in real space, so if you had a real space, right? Not if you have a real space. If we think about the real space, I think what you're hinting at is Bloch oscillations, right? Okay. So first of all, Bloch oscillations are in this piece, which will average to 0, right? But also Bloch oscillation, think about it for a second. Bloch oscillation means that you're pulling on the particle, and now you're driving it through the band structure, right? And the velocity is going to at first go in the direction of the force and then turn around, right? That's just a Markov conservation of energy. So this is the motion that will happen along the omega direction. So the particle will actually carry out Bloch oscillations like this. And those are the ones that average out over the cycle. Right, so when you integrate over a whole cycle, this ends up being 0 just because the dispersion is periodic in momentum. But it was surprising to me. It's just conservation of energy. The particle just cannot go away from that energy step. Other questions? So you really need this topology, this wrapping of the effective spin, to get this particle to move perpendicular to the effective force. All right, so this is the motion in synthetic dimension. Here's some more graphics on this. So we have a particle in a synthetic dimension. It looks like this particle, the spin, has a force applied to it. What does it do? It moves perpendicular, like a particle in a magnetic field. What is this magnetic field? It's the result of the topology of the underlying band that are used to create the synthetic dimension. Now, the motion is such that it conserves energy. So omega 1 dn1 dt plus omega 2 dn2 dt. Omega dot, this vector is 0. But each term here describes a work that the drive does, right? Omega 1 dn1 dt is how much work drive 1 did. Omega 2 dn2 dt is how much work drive 2 did. But we know what this velocity is. So dn1 dt is just the Berry curvature times omega 2. So omega 1 dn1 dt is the average Berry curvature times omega 1 times omega 2, which means that the work that's done by one drive that goes to the other drive is just the product of the frequency times 1 over 2 pi, times the Chern number over 2 pi. The topological frequency converter. For the experts amongst you, this is really could be mapped to the fact that topological two-dimensional band structure have a sigma xy that's quantized. And this is the quantized motion perpendicular to a force or perpendicular to an electric field. But this results in a quantized energy pumping. And this is topological energy pumping or topological frequency conversion. Nowhere did I tell you what the two frequencies were, except I wanted them to be incommensurate, right? So I can use this principle to convert any frequency to any other frequency, as long as the frequencies are small relative to the drive Hamiltonian. So this is the idea of a new control. So this suggests that topology, when taken out of its spatial the original playground, the spatial original playground where it was conceived, taken into dynamics, gives you different abilities to control dynamical phenomena, in particular driven systems. So what did we achieve? Again, this we have this spin that takes one beam, amplifies it, takes another beam, takes away energy from it. And the question is, can we realize this with some material? And it seems like the right materials to realize such Hamiltonians are, again, Weil semimetals. Each electron has a Hamiltonian that looks like sigma dot some vector. And when you take all the electrons together, there will be some cancellations, there will be some enhancements. And this is current work, trying to figure out whether a Weil semimetal that breaks inversion symmetry can actually realize this topological photonic pump. All right, maybe this is a good time to close. So let me conclude. What did we do? We did a lot. So we're talking about new control paradigms of topological phases, new topological bosons, topolaritons, maybe new class of photodetectors. I think the diagrams will appear for each one of those. And a new idea of how to control photon conversions and photon amplifications, which might give rise to a new class of optical parametric amplifiers and nonlinear photonic materials to be used for amplifications, particularly in the terahertz regime. That seems to be the regime that's right for that. It's a good time to stop. Thank you very much. Questions? Yeah.
You talked about periodic driving, you talked about spin, you talked about the frequencies not being commensurate. Does this paradigm give you anything related to time crystals?
To time crystals. It's very interesting. It's related.
Okay.
It's really related. So there are parallel works to this. I was working a lot on dynamics recently. So there are two places where there was overlap with time crystals. So one thing, remember I showed you the forbidden Majorana states in the beginning, Kitaev model? So back when we did this Fouquet topological insulator work, I think it was Takuya Kitagawa that realized that, wait, we can also think about irradiating one-dimensional Kitaev model and then creating Majoranas, so creating a phase transition between trivial Kitaev model into the phase where it's not trivial and has Majoranas. Then we did this, and we discovered that when we do this, we can actually get two types of Majoranas. One at 0 frequency, and the other at omega over 2, at half frequency. Why? This is not the right diagram exactly, but you can think about this energy axis as being periodic, 0 energy minus frequency over 2 plus frequency over 2. But just like a Brillouin zone is periodic between minus pi over a and pi over a, this energy Fouquet zone, if you wish, is periodic from minus omega over 2 to omega over 2. So energy 0 is particle Hall symmetric. Energy omega over 2 is also particle Hall symmetric and can host a Majorana. We showed this in 2011, I think. That Majorana state is the time crystal. When you dress it with interactions and disorder, this half frequency, right? It's a state at half frequency. That's the period doubling of the time crystal.
If it's been demonstrated experimentally, if you do that, that would be a new demonstration of time crystals?
Yeah, it's equivalent. It's equivalent. And if you think about the models that we use for time crystal, we're a transverse field Ising model, which is the spin dual of the Kitaev model P-wave superconductor. So it's really one-to-one. And I think they didn't understand this as they were doing it. We didn't understand that we can do this either. Now, the second thing is in the multiple drives, you have multiple drives. You can actually create multiple flavors of Majoranas at the various omega 1 over 2, omega 2 over 2. And so we thought about it as Majorana multiplexing. You have one Kitaev wire, you irradiate it, it starts having like many channels of Majoranas that don't talk to each other. And actually, Drew Potter and I think Roman Vasseur actually did the simulation for a multiply driven time crystal. And they found peaks, spectral peaks at omega 1 over 2, omega 2 over 2, etc., coexisting even though there's no time translational invariance anymore. So there were two overlaps. But yeah, clearly those are related topics. Very good question. Sure.
So the Brillouin zone in your last construction is determined by two frequencies, right?
Not quite. So we'll go on and finish the question. Let's see.
So
this.
maybe
Right?
ask you. If I double one of the frequencies, what happens to the Brillouin zone?
So look, the Brillouin zone was just, there was some kx parameter in the Hamiltonian, there was a ky parameter in the Hamiltonian, right? Now I replace them with linear in time function, right? So this is like a force. Look, k dot is omega. Momentum dot is omega. So it's like I had a particle in my Brillouin zone and I apply the force to it. That's why the question about Bloch oscillation is exactly the right one. So the Brillouin zone doesn't change. What changes is the track that the particle will do through the Brillouin zone. Right, so it's like, I have a periodic function, and now I can put time in that periodic argument. But, right, but I see where you're coming from, because depending on what omega is, if I think of the Brillouin zone in terms of time, then it'll change, right? But then if I think about it as omega t as being, yeah. Exactly. Exactly. So what you need to think about is the Hamiltonian is periodic, so it's a function of phi 1 and phi 2, two angles. And in those angles, it's always from minus pi to pi. And now you can relate those angles to time whichever way you want.